This is second half of lecture 17 for EP1. In this half, we will continue discussing rotational motion, and we will look at it from a different angle. This angle is rotational energy. Just to remind you how energy works for the regular translational motion, if you have an object that has mass m, and if this object experiences a force over some distance, then towards the end, this object will have higher velocity. And we know that the work that the force did on the object is equal to the change in its energy. And the energy is mv²/2. So objects that are heavier and that move fast have higher energies. We know that if there are no friction forces or other non-conservative forces, then energy is conserved. And that's very helpful to know because it helps you to solve many physics problems. So for example, if you have an object here, let's say 2 meters above the ground, and if this object falls, then if they ask you what's the velocity of this object just before it hits the ground, you can solve it very easily using conservation of energy. You will say in the beginning I had potential energy mgh. Towards the end, I had kinetic energy mv²/2. And since energy is conserved, those two must be equal. Your mass will cancel out and your velocity will turn out to be twice gh. What we will do now is we will think about how objects that rotate contribute to this. So let's say you have this box, and this box is suspended on a rope, and there is this pulley. As this box falls down, it will be losing its potential energy because it gets closer to the ground, and it will be gaining its kinetic energy. But what's another thing that's happening here that we kind of have ignored so far is that I have a pulley here, and as this box falls down, the pulley will start spinning, and the more this box falls down, the faster this pulley will spin. And spinning a pulley requires some energy, and that energy has to come from somewhere. Some amount of energy that this box had in the beginning, some amount of that mgh, will go into its velocity, but there will be some part that will be spent on rotational energy of the pulley. So let's call it rotational energy. And because of that, by the time this box gets to here, it will have a lower velocity than it would have if there was no pulley or if the pulley was massless. And that's because its initial potential energy is now redistributed into its kinetic energy, but some part of it is wasted on the rotational energy of the pulley. We will see in a little bit how this works exactly in details. Just to give you an expression for rotational energy of an object is equal to its moment of inertia times its angular velocity squared divided by 2. So this is very similar to the kinetic energy where you had mass times velocity squared/2. We have talked about this already. We know that the moment of inertia is kind of like mass when it comes to rotations. And angular velocity is obviously the equivalent of velocity when it comes to rotations. So this is the key formula that you have to remember. rotational energy, the more moment of inertia a body has, the more energy it has, and the faster it spins, the more energy it has. Before we start solving problems that involve energy conservation, I want to do a few simple questions that have to do with the moment of inertia, because moment of inertia is kind of the new concept here. Conservation of energy we are already familiar with. So let's start with question 17.1. That's slide number 7. This is a question that I asked you at the end of lecture 16. In this question, I have 3 disks that look like this. They have 2 layers, inner layer and the outer layer. And the same force is applied here and here and here. And for disk number 1, outer layer is denser. For disk number 2, inner layer is denser. And for disk number 3, again, the outer layer is denser, but otherwise they have the same mass. The question is, which disk is easier to rotate? Or in other words, if I applied this kind of force for, say, 5 seconds, which disk would be rotating faster? So why don't you pause the video, think about this, pretend this is an iClicker question, and then come back. Okay, so the question was, which disk is easier to rotate given this arrangement? And now if I look at disk number 1 versus disk number 3, you can see that the only difference here is where the force is applied. For disk number 1, the force is applied at the outer edge, and for force number 2, it's applied inside in here. And if this is our axis of rotation, then I know that my torque is equal to the moment of inertia times angular acceleration. So if I have more torque, I will have more acceleration. And I also know that my torque is equal to the force times distance from the axis of rotation times the angle. I have the same force in both cases. I have the same 90-degree angle in both cases. But for disk 1, this force is further away. So disk 1 will experience more torque. Therefore, disk 1 would be easier to rotate. So disk 1 beats disk 3. Now let's look at disk 1 versus disk 2. In this case, I have the same force, the same angle, the same distance. So I have the same torque. But the difference here is in the moment of inertia. So moment of inertia, if you have high moment of inertia, you are more difficult to rotate, and the other way around. And here, even though we don't have exact formulas and numbers, it's easy to guess which disk will have higher moment of inertia. Just to remind you, the moment of inertia usually goes like this. It goes like mass times r squared. So if you are heavier, you have higher moment of inertia. And if your mass is further away from the axis of rotation, you have higher moment of inertia. And these two disks, they have the same mass, but disk number 1 has its mass on average further away from the axis of rotation than disk number 2. And because of that, I will conclude that disk number 1 has higher moment of inertia, therefore it's more difficult to rotate. Disk 2 is easier to rotate because most of its mass is closer to the axis of rotation. So disk 2 beats disk 1, and my conclusion is that disk 2 is the easiest disk to rotate given this setup. Now let's move to question number 17.2, which is a similar question. In this question, you have, what do you have? You have 3 disks. One of them is small but heavy, 1 meter, 26 kilos. The second one is larger but lighter, 2 meters, 7 kilos. And the third one is even larger, even lighter, 3 meters and 3 kilos. The question is, which disk is harder to rotate around the middle? Now, this is not easy to guess because their sizes and masses change at the same time. So we will have to use exact formula. And the formula that I'm looking for is the formula for the moment of inertia of a disk rotating around its middle. So moment of inertia of a disk, I will look into the textbook. There's a table and okay, list of moments of inertia. And this table tells me that if I have a solid disk of radius r and mass m, then its moment of inertia is half of mr squared. Half of mr squared. Okay, good. So let's compute this for all three of them. For the first disk, I have half of 1 kilo, 26 kilos times 1 squared. Here I have half of 7 kilos times 2 squared. Here I have half of 3 kilos times 3 squared. This is 13. This is 14. And this is 27 divided by 2, that's 13.5. Is that? Yes, I think that's true. Okay. Okay, so it looks like disk number 2 is the one that's most difficult to rotate. And it has the worst balance of the mass and how far away you are from the origin out of these three. Okay, let's go to problems now. I have two problems, problem 17.1 and problem 17.2. Problem 17.1 is actually one of your studio problem solvings. So I'm not gonna solve it completely. I will just help you out by giving you a few ideas. So what you have here is you have a table, and there is this spherical shell with some mass and some radius. You have a pulley with some moment of inertia and some radius. And you have a mass. And what will happen here is that if you let it go, this mass will start moving down. And the pulley and the sphere will start rotating because they are all connected with the rope. Now, this problem would be difficult to solve if I had to compute all the forces and torques. What I will do is I will try to solve this problem by applying energy considerations. So in the beginning, what I will do is I will pick this as my 0 level for my potential energy. And I will say that in the beginning, my energy was 0 because nothing was moving, nothing was rotating, and nothing had potential energy. So in the beginning, my energy was 0. Now, if there are no non-conservative forces like friction, then my energy should be conserved. So when this box starts falling, what happens here? When this box starts falling, it will be below the 0 level now. So it will have some negative potential energy. And if it moves by distance h, it will have an energy of negative mgh. At the same time, it will start gaining some speed. It will have kinetic energy, which is mv squared over 2. So these two must cancel out each other because energy must remain zero. It was zero in the beginning. And if I rewrite this, then I will get a familiar equation, mgh is equal to mv squared over 2. If there was no sphere and no pulley, then I would have this equation that would tell me that the more I drop, the more velocity I gain, which makes sense. But now what's different here is that I do have a pulley and I do have this spherical shell. Both of them will start spinning as my box falls down, and they will take away some energy from the box. So my true conservation of energy is that the energy is zero at the beginning, and then I have my negative mgh, then I have my mv squared over 2, but that's not all. I also have rotational energy of my pulley, energy of the pulley, let's say, plus energy of the spherical shell. Those two are rotational energies, so I can write them as moment of inertia of the pulley times angular velocity of the pulley squared divided by 2 plus moment of inertia of the spherical shell times angular velocity of the spherical shell squared divided by 2. So now if I move this negative mgh to the other side, I will get an equation that reads mgh is equal to mv squared over 2 plus I of the pulley, omega of pulley squared divided by 2 plus I of the sphere times omega of the sphere squared divided by 2. Again, this makes sense. This tells me that the more farther I drop, the more energies I get into my box, into my pulley, and into my sphere. Now, let's see what I know from here and what I don't know. So I do know, I think in the problem, you're given H, you know H, you know G, you know the mass. You know, so you know this mass, you know the moment of inertia of the pulley, and you don't know the moment of inertia of the sphere, but you can find it easily. So this is a spherical shell. You can look up formula for the moment of inertia of a spherical shell, and you can find it. It's a simple formula. And so what you don't know here is the velocity, angular velocity of the pulley, and angular velocity of the sphere. So what I will do is I will stop here. But one more hint that I will give you is that since this rope is not slipping, then if you know the velocity of your box, that kind of fixes the velocity of your pulley, and it fixes the velocity of your sphere. They cannot all have some random velocities. And the formula to remember is the formula that relates linear speed with angular speed. So if you have a disk, and if you have a point on this disk, then the linear velocity of this disk and the angular velocity of the disk are related by, let me think here, V is equal to omega R. So this is the relationship that you will use to guess how the angular velocity of the pulley and the sphere are related to the velocity of the box. And if you cannot figure this out, we will have a Zoom help room session on Friday, so please join on Friday, 12:30. Okay, now I want to move to problem 17.2. In this problem, what you have is you have two boxes and a pulley. These boxes have the same mass, So M. And you know the moment of inertia for this pulley, it's I. So you have to find two things. You have to find the tensions, tension 1 and tension 2. And you have to find the box's acceleration. Okay, so what do? Well, we start in these kind of problems. We always start by writing down Newton's second law for everything, all the objects that are involved. I will start with this object, the hanging object. Let me call this object 1. So for box number 1, I have two forces. One force is mg, and another second force is T1. These are the only two forces. This object is moving downwards with some acceleration. So the Newton's second law for this box reads mg minus T1 is equal to m times a, mass times acceleration. Now let me write exactly the same thing for this object. Let me call this object 2. So what kind of forces do I have on object 2? I have mg. Let me draw it here actually. I have mg. I have normal force. mg and normal force are balanced because there is no up and down motion. And I have my tension. Let's say there is no friction. If there is no friction, then my Newton's second law tells me that T2 is equal to mass of my box times its acceleration. Now let's think about the pulley. So I will draw my pulley here. So how many forces are acting on this pulley? I have two forces. There is this force T1. There is this force T2. And the pulley is spinning around this point. So since I have a rotational motion, my Newton's second law, or the equivalent of Newton's second law, is now that the torque, the net torque, is equal to the moment of inertia times angular acceleration. Let's think about what my net torque is. I have two forces. So there is torque of force 1, and there is the torque of force 2. For force 1, I have a negative sign because force 1 is trying to rotate me counterclockwise, sorry, clockwise. I have force T1. It's some distance r from the axis of rotation, and it makes a 90-degree angle. For force 2, I have exactly the same thing except a change in sign. I now have a different sign. And so T2 times R, this is my net torque. And my net torque is equal to my moment of inertia times my angular acceleration. Okay, I have three equations now. This is my one equation. This is my second equation. This is my third equation. So let's look at everything that I know first. I know my masses, and I know G. I know this mass here. I know, how the pulley is. I know pulley's moment of inertia and its radius. And what is it that I don't know? I don't know my tension, T1. I don't know my acceleration. I don't know my T2. And I don't know my angular acceleration. So it looks like I have three unknowns and, four unknowns 1, 2, 3, 4, and only 3 equations. So that's not enough. I need one more equation. And this one more equation will be the equation that will relate the accelerations of the boxes to the angular acceleration of the pulley. So acceleration of the boxes are equal to the acceleration of this imaginary point on the rope. And I know that if I have a point on the rim of my disk moving, then its acceleration is related to the angular acceleration by linear acceleration is angular acceleration times r. So this equation links acceleration of my boxes to the acceleration of the pulley, and I was able to write down this equation because I knew that the rope wasn't slipping, that the amount by which this rope moves is basically equal in some sense to the amount of angle that this pulley rotates by. Okay, now that I have all these equations, what I will do is I will write them. I will have to erase some stuff, so let me erase this here. Let me write all the equations on top of each other. So I have mg minus t1 is equal to ma. I have t2 is equal to ma. And I know that my acceleration is angular acceleration times r. So I can, from here, I can write angular acceleration is linear acceleration divided by r. So I can replace this by linear acceleration divided by r. So I will erase a bit more stuff here to give me some room. I have these 3 equations, and I have 3 unknowns, t2, t1, and acceleration. So from now on, this is just algebra. What I will do is I will first solve for t1 from this equation. From this equation, I know that t1 is equal to mg minus ma. And then what I will do is I will substitute t1 and t2 in here. So instead of t1, I will substitute this. I will get negative mg minus ma times r plus, for t2, I will substitute this, plus ma times r. This equals to I acceleration over r. So after opening these brackets and doing some simplification, I will get negative mgr plus twice mar is equal to I a over r. And I will solve this for acceleration. Let me rewrite it as twice mar minus I a over r is equal to mgr. And from here, it follows that my acceleration is mgr divided by twice mr minus I over r. Okay, this is my acceleration. And this equation may not be as easy to analyze when you look at it at first, but some of these things make sense. So for example, if I have more g, then I have more acceleration, makes sense. If I have more moment of inertia for the pulley, what's happening here? Yeah, so one thing to keep in mind is that this thing, for some values of I. If I is too large, then this number could become negative, which means that acceleration would then become negative. Oh, shoot, I made a mistake, sorry. You know what, I made a mistake in sign, yeah. So this is why it's useful to analyze your solutions, because it's easy to catch mistakes. Okay, I'm sorry, I will go back. I will erase all of this. I'm not gonna re-record this video because I think these kind of mistakes are instructive, so I want you to be on board. Okay, so here is what I do. The mistake that I made was that in here, when I wrote this equation, I had an acceleration, and this acceleration should have been negative. That's something that I forgot. This acceleration should have been negative because if you look at my pulley will be rotating clockwise, and I'm following a convention according to which clockwise rotation is a negative rotation. That's how I put my negative sign here and positive sign here. Yeah. So I should have had a negative sign here. I forgot to put it, and that's why my solution didn't make sense. So let me resolve this problem again. It's just the sign. Everything else is correct. So this is my T1. This is still correct. I will plug in T1 and T2 in here, and I will get negative mg minus ma times r plus ma times r is equal to negative I a over r. I will open my brackets, negative mgr plus twice mar is equal to negative I a over r. And then I will rewrite it as twice mra plus I a over r is equal to mgr. And from here it follows that my acceleration is equal to mgr divided by twice mr plus I over r. Yep. So this is my acceleration, and now things make sense. So if you look at it, so for example, if you have more g, you will have more acceleration. However, if you have more I, which means that if your pulley is more difficult to rotate, then since this is divided by I, you will have less acceleration. And both of those things make sense. Now I'm happy with my solution. Okay, that was all that I wanted to talk to you today about. And again, to remind you, we have a Zoom help room session on Friday, 12:30 to 2:30.